My name is Colin Ballantyne. I'm Emeritus Professor of Physical Geography at the University of St Andrews. And in this evening's talk, what I'll be doing is examining some of the changes that have taken place in Arctic landscapes over the past few decades. So what do you think about when the word Arctic is mentioned? For many people, it carries connotations of bitter cold, strong winds, being locked in darkness throughout the winter. It carries connotations of snow and ice and of course polar bears. But the Arctic is actually a place of great variety, and we can recognise about 3 different major regions within the Arctic latitudes. The first of these is the polar desert. This is an area of great aridity, usually less than about 200 millimetres of precipitation per year, that occurs in the farthest north latitudes, in places like northern Greenland and northern Ellesmere Island in the Canadian Arctic archipelago. It's a zone where very little grows, just mosses and lichens covering up the stony Earth's surface. Moving further south, we get into a semi-arid area, which is the Great Tundra Zone. Now, the tundra occupies an enormous portion of the land surface, about 11 million square kilometres, or slightly greater than 7% of the Earth's land area. And it's characterised by a lack of trees and low shrubs and grasses vegetation. In fact, as you can see from this picture here, much of the tundra actually looks a bit like parts of the western or northern Isles of Scotland, such as the Outer Hebrides or Shetland. Then encircling the tundra at lower latitudes and spreading for an enormous area across Siberia, northern Russia, northern Scandinavia, the Canadian Arctic and into Alaska is the Great Taiga or Boreal forest. This is the major biome or vegetation type of the Arctic and subarctic. It occupies more than 17 square kilometres, or more than about 11% of the Earth's land area. And it consists of conifers, larches, spruces, pines, interspersed with multiple wetlands. So these are our 3 types of Arctic landscape. My own association with the Arctic goes way back to 1974, when I formed part of a research team from McMaster University in Canada that was investigating the hydrology of high Arctic rivers, about which we knew very little at that particular time. In this picture here, you can probably identify which one is me, not least by the unusual dress code. Wearing a kilt in the high Arctic, however, is not to be recommended on account of the fact that mosquitoes get absolutely everywhere. Now, as you can see, of course, in the intervening decades, I've changed quite a bit. And the Arctic also has changed. It's changed quite considerably in certain respects. And this is because, of course, the Arctic is warming up. You can see from this map, which documents changes in global temperature over the period 1979 to 2019, that so-called global warming affects different parts of the Earth's surface differently. As you can see, warming is concentrated in northern high latitudes. And as a rule of thumb, the Arctic has warmed 2 to 3 times greater than the average for the rest of the planet. This effect, this heightened warming of the Arctic latitudes, is known as Arctic amplification. We're not entirely sure why this occurs. Various climatologists have got different explanations. But there's one simple explanation that all of them have adopted. And that's due to what we call radiation feedback. If you look at this slide here, you'll see that there's a progression. If we get atmospheric warming taking place at the top of the slide, This automatically will result, obviously, in a reduction in summer snow and ice cover. But snow and ice are very good at reflecting solar radiation back out to space. So if the amount of snow and ice cover is reduced, then clearly more radiation is going to be absorbed at the surface. This results in increased heating at the surface, which of course results in atmospheric warming. So we've set in train a kind of vicious circle whereby an initial period of warming is self-sustaining. It tends in fact to accelerate through time by reducing snow and ice cover. Now the effects of Arctic amplification of warming are most evident in terms of changes that have taken place in the cover of sea ice in the Arctic. But sea ice cover is a bit complicated because of course it changes seasonally. The greatest sea ice cover occurs at the end of the winter, usually in late March or early April. The smallest amount of sea ice cover, of course, occurs at the end of the summer, after the melt season, usually by the end of September. So if we take a snapshot of this for end of winter and end of summer sea ice extent in 2016, you can see the difference between the two. Sea ice cover is fluctuating seasonally. Winter sea ice cover, on the other hand, hasn't actually changed terribly much in the past 20 or 30 years. But summer sea ice cover is now only about 50 to 60% of what it was in about 1980. And here's an interesting satellite image, and it shows the extent of sea ice cover in 2020 compared with the average extent, the yellow line, in the period 1981 to 2010. And as you can see, even when compared with that average, sea ice cover has now shrunk markedly until it is only a fraction of what it previously was. If we put this on a graph, you can see that winter sea ice cover hasn't changed very much since 1980. It's only changed by about 10%. But summer sea ice cover, on the other hand, has reduced by about 50 to 60% of what it previously was. Now, a few years ago, I made a prediction at a RSGS talk that it would soon be possible for somebody to kayak to the North Pole. And I maintain that this is the case. I think we'll probably see this on our television screens within probably 5 or 6 years or so. And the reason that I'm confident about this is because the sea ice cover is not only getting less by year, but it's also thinning every year. Where sea ice manages to survive the summer melting and accumulate more ice cover in the following winter, it gets thicker and thicker. So old sea ice that's been around for 2 or more years, tends to be thicker than new sea ice that is formed in a single winter. And as you can see from this graph, the amount of old sea ice, particularly sea ice that's 3 or more years old, has almost disappeared. And so the summer sea ice cover that now exists is very much thinner than it previously was and is liable to disappear more rapidly. What about that other source of ice, glacier ice? Well, much of the Arctic does not support glacier ice. It's simply too arid. There's not enough snowfall to nourish glaciers. The main exceptions, of course, are the Great Greenland ice sheet and the numerous smaller ice fields and ice caps that occupy places like Svalbard, the Russian Arctic Islands, Ellesmere Island, Axel Heiberg Island, and so on in the Canadian Arctic. These smaller glaciers generally consist of ice fields that are drained by large outlet glaciers. And here the picture isn't so grim. Interestingly, I have recently visited, using Google Earth, the same glacier that I worked at way back in 1974 on Ellesmere Island. And I discovered that it in fact had not retreated at all. It was almost stationary, almost at the same position that it was over 4 decades ago. And this is true of many of the smaller ice fields and ice caps. They tend to be thinning a little bit, but glacier retreat is not marked, much less, for example, than glaciers in the Alps or Norway. And this is due to the temperature of the ice. These Arctic glaciers contain ice that is well below freezing point. And this means, of course, that they are much less likely to retreat. You have to heat up the ice within the glacier before it can start to melt. But the big ice mass that concerns us most, of course, is the Great Greenland Ice Sheet. And it's almost difficult to get round the dimensions of this. The Greenland Ice Sheet covers an area of about 1.7 million square kilometres. It contains about 2.8 million cubic kilometres of ice. Now let's just stop for a minute and think about what a cubic kilometre of ice actually looks like. And yet we've got 2.8 million of these locked up within this ice sheet. And if this were all to melt, sea levels would rise by about 6 metres. So the health of the Greenland ice sheet is something that concerns us. We do know that it is losing mass. You can see from this graph here that between about 2000 and 2016, it lost about 4,000 gigatons of ice. A gigaton is 1 billion tons. But that's only about 1/10, but the annual loss of about 286 cubic kilometres per year is only about 1/10,000th of the overall mass of the Greenland ice sheet. And so if the present rate of loss was sustained, it would take 10,000 years before we lost all the ice in the ice sheet, which is perhaps encouraging. Present losses amount to about 0.6 of a millimetre per year in terms of sea level rise. So where is all this ice going? Well, some of it is being lost at the calving margins, where the Greenland ice sheet outlet glaciers terminate in the sea. Because the Arctic Ocean and other oceans in high latitudes are warming up, rates of calving tend to be accelerating. And as a consequence, icebergs are breaking off more rapidly. When this happens, the glaciers that are draining the centre of the ice cap tend to draw down the ice on the ice sheet itself. And you can see this most spectacularly by comparing images of some parts of the Greenland ice sheet taken way back in 1935 with those taken more recently. And here you can see a fjord that was filled with glacier ice in 1935 and is now completely ice-free, with tributary glaciers retreating to their sources. Now, the changes in sea ice cover and in glacier extent can be readily monitored from satellites. We have satellites passing over the Arctic on a daily basis, so all of these changes in ice cover can be readily monitored. But the next big change in the Arctic is effectively invisible. And these are all probably the most important changes in the Arctic. They involve changes to permafrost. So what exactly is permafrost? I'm sure you've heard the word. You probably haven't thought too much about what it actually means. Permafrost is simply ground that remains below 0 degrees centigrade throughout the year. In other words, it's perennially frozen, though ice may not be present. Sometimes I'm asked what permafrost looks like. I remember asking some students that, and they once said, well, it looks a little bit like sort of green cheese. But it's not like green cheese. Permafrost is a rock. It's very solid and very hard and very cold. Amazingly, permafrost, or the permafrost zone, where at least patches of it occur, occupies about 24% of the land area in the Northern Hemisphere. A quarter of the land area almost is underlain by permafrost. In the areas of the deepest shading in this slide, we have continuous permafrost. That's where effectively permafrost underlies the entire land surface. Farther south, we've got a zone of discontinuous permafrost where it occupies between about 50 and 100% of the land surface. And further south from that, we've got an area of what we call sporadic permafrost, which is where permafrost occurs in small patches here and there. And you can imagine why it occurs in some places and not in others. If you just consider a hill slope, we might find that there's permafrost on the north side of the hill, but none on the south side, which is facing the sun. The actual area underlain by permafrost at present is about 16% of the Earth's land area. And that's much greater than the amount that supports glacier ice, which is only about 10%. But the reason it's difficult to monitor permafrost is that it doesn't extend to the ground surface. Instead, it's overlain by a layer that thaws out every summer and then freezes from the top every winter. And this layer is called the active layer. The top of the permafrost therefore lies at some depth under the surface. Active layer depths vary depending on where you are in the Arctic. In the high Arctic, they may be as little as about 40 centimetres per year. Once we get down to the subarctic, they may be something like 2 metres of thawing every year. So a very simple way of actually assessing whether the permafrost is thawing is simply to put a pole through the active layer at the end of the summer melt season and find out whether the active layer itself is getting any thicker. Because if the active layer is getting thicker, that means the top of the permafrost is progressively melting. And this has been done by something called the Circumpolar Active Layer Monitoring Programme over about now 30 years. And as you can see, the results of this programme, and I've plotted this for about 8 sites, show that the end of summer active layer depth tends to vary from year to year. But in general, the overall trend is downwards. The active layer is getting thicker, and so the top of the permafrost is obviously progressively thawing out. It's not rapid. You can see from this graph that it's only been between about 10 and 30 centimetres in the last 20 years on average. Moreover, it's likely to slow down as the top of the permafrost gets deeper, simply because it's more difficult for heat reaching the surface to penetrate to greater depths. There's the other way of assessing the health of the permafrost. Is a bit more complicated, and that is to put in boreholes and measure the temperature of the permafrost at depth. And if we do this from year to year, we can see that indeed the permafrost is warming up. However, most permafrost sites in the high Arctic are still well below 0 degrees centigrade. That permafrost is still relatively healthy. It's in the discontinuous permafrost zone, where permafrost is only just below freezing point or melting point, that there's a danger that it starts to thaw out. Now, why should this concern us? Why should the changing temperature of the ground be a matter of concern for us? My next picture here shows a permafrost section at a place called the Untitled River in Alaska. And what you can see from this is that it contains a huge amount of ice. The vertical columns are things we call syngenetic ice wedges. They're almost exactly pure ice, and in between we've got icy silts. As at Itkilik, 90% of what you're seeing at the side of this river is ice. And what this implies, of course, is that if this permafrost thaws, then there's going to be massive subsidence of the terrain. And this is happening on a widespread course throughout very much of the Arctic. In the Taiga zone, we get the formation of thermokarst bogs. Thermokarst, incidentally, is a term we use to describe those landforms that are produced by thawing and subsiding permafrost. And these thermokarst bogs are progressively linking up and deepening. Eventually they form shallow lakes, and eventually, as the ice underneath progressively melts, they form deeper lakes that join up. So there is considerable loss of habitat and destruction of the taiga forest. And a similar thing is also happening in tundra landscapes. Here again we've got the formation of bogs and fens as areas of tundra begin to subside and support surface water. And we also have extensive areas of thermocourse lakes. Now, thermocourse lakes aren't new. They were certainly around long before any form of global warming took place. But they're now beginning to expand, to join up with each other, and new ones are forming. In fact, at the moment, about 25% of Arctic lowland landscapes are covered by more than 61,000 individual thermocourse lakes, some of them very large. Finally, thawing of the permafrost has had the effect of destabilising slopes, and this has given rise to some particularly dramatic landforms. One of these is what we call megaslumps, or to use the technical term that we geomorphologists use, retrogressive thaw slumps, such as this one beside the Selivik River in Alaska. The back wall is about 40 metres high, and it's progressively retreating by about 10 to 20 metres every year. So these slumps start off small and gradually expand into the landscape. Moreover, this is actually quite a small megaslump. Some of those that occur along the Siberian coastline are very, very much larger. Several extend over several square kilometres, and locally, the area of ice-rich permafrost that's degrading at the head of the slump is anything up to 100 metres high. The Arctic Ocean is surrounded by a number of relatively shallow seas: the Kara Sea, the East Siberian Sea, the Chukchi Sea, the Barents Sea, the Beaufort Sea. And over wide areas, these are low-lying coastlines of sediments that are, of course, underlain by permafrost. This next picture here shows the Laptev Sea coastline in northern Siberia. And what you can see is that this is extremely icy. The vertical columns again are ice wedges, and in between we've got ice-rich silts. Probably about 50% of the area in between consists of ice. When we get coastal storms, then of course the sea at high tide reaches into the base of this icy cliff and begins to thaw it. As a result, of course, the cliff collapses. All this icy sediment simply melts and gets washed away by the sea. And so simply by this simple process, we end up with marine retreat, coastal retreat, of the order of a few hundred metres per year. Every time the high sea undercuts the icy cliff collapses, and so we get accelerated coastal erosion. And even worse than that is where megaslumps develop on the Arctic coastline, as here in the Beaufort Sea on the north of Alaska. And you can see these are rapidly eating away the surrounding land area. Now, in the Arctic, virtually all settlements, whether in Siberia or Alaska or the Canadian Arctic, are either on the sea or on the shores of major rivers. And the effects on Arctic coastal settlements of such rapid erosion has been really dramatic. Because we've lost most of the summer sea ice cover, when there are storms, these are now much more violent, because the fetch, the area over which open water operates, is now much greater than it once was. Already, coastal erosion has caused extensive damage to buildings and infrastructure around the margins of the Arctic Ocean. Entire buildings have been swept into the sea. There's another factor operating here, and that is because summer sea ice is beginning to be reduced year on year, then individual storms tend to be more severe. This is because the open water fetch is progressively increasing around the margins of the Arctic Ocean. And entire communities within the Arctic have either had to be abandoned or they have had to be relocated as a result of this accelerated coastal erosion. But why should we worry about this? After all, the Arctic is a remote area, it's far away, and the population, the total population north of the Arctic Circle is only about 4 million, which is a tiny fraction of a global population that's approaching 8 billion people. But we should, because the thaw of permafrost has another consequence. Much of permafrost contains partly decomposed organic matter. And this plant matter, this organic matter, is stable so long as it's locked in frozen permafrost. But when the permafrost thaws, it begins to experience microbial decomposition. And this produces greenhouse gases, both carbon dioxide and methane. Carbon dioxide tends to be produced where the thawing soil has access to free oxygen. Methane tends to be produced in lakes and waterlogged locations which are anoxic, in other words, there's no free oxygen. And methane, as you probably know, is a much more powerful greenhouse gas than carbon dioxide. Both gases are, of course, invisible, but we can actually see methane being produced from Arctic lakes. Such lakes contain large bubbles. These aren't bubbles of air, they're bubbles of methane. And if we break the ice and apply a match, then the methane burns and produces carbon dioxide. Due to thawing of permafrost, the Arctic is a major source of methane in the atmosphere. And even though the concentration of methane is much less than that of carbon dioxide, it's a much more powerful greenhouse gas. Molecule for molecule, it's about 26 times as potent as carbon dioxide in the atmosphere, and is responsible for a significant amount of global warming. So as far as the rest of the world is concerned, the most important aspect of the changes taking place in the Arctic are related to thawing permafrost. And we can see that this takes the form of a rather alarming feedback loop. Starting again at the top with atmospheric warming, we get thaw of permafrost. This in turn is resulting in microbial decomposition of organic material that was previously locked or frozen into the permafrost. Microbial decomposition releases carbon dioxide and methane, and this in turn contributes to atmospheric warming. So we have another vicious circle taking place, whereby an initial change is actually self-reinforcing. And I think the alarming thing is here that there's a huge amount of terrestrial carbon within permafrost. It's estimated that it lies between about 1,330 and 1,580 gigatons. Remember, a gigaton is 1 billion tons. And moreover, about 1,000 gigatons, or more than 1,000 gigatons, lying within about 3 meters of the surface. And what this implies is that even if humanity manages to achieve its goal of net zero in terms of carbon emissions, the thawing permafrost is going to continue to produce greenhouse gases into the atmosphere and contribute to warming. Now that might seem quite gloomy. Is there any good news? Well, there is some, but it's a bit difficult to assess. First of all, under a warming climate, vegetation growth in the Arctic is liable to be enhanced. We've got warmer summers, a longer growing season, and indeed the decomposing organic matter itself contributes nutrients for plant growth. And this means that the Arctic vegetation in the tundra and the taiga is growing faster, and so it's absorbing more carbon dioxide from the atmosphere. Secondly, the rate at which permafrost thaws is likely to decrease with depth, simply because it takes longer for heat at the surface to penetrate to greater depths. And finally, there's some laboratory studies which suggest that the rate of microbial decomposition starts rapidly, but then tails off fairly spectacularly through time. So to some extent at least, the Arctic is self-regulating the release of carbon dioxide, although it's unlikely to do so indefinitely. I'd like to leave you now, and I thought that no talk on the Arctic would be complete without a picture of the midnight sun. So here's a picture I took a few years ago at a place called Eastfjord Radio in Svalbard. Eastfjord means ice fjord and was named by the first visitors to this area about 200 years ago. As we can see, however, there is now no ice in Eastfjord, even in April when this midnight sun photograph was taken. Let's fast forward. What's the Arctic going to look like in 2050? Well, it's still going to be cold. It's still going to be locked in winter darkness. We'll still get sea ice forming in winter, though probably not in summer. Depending on the level of anthropogenic greenhouse gas emissions, there will still probably be extensive areas of glacier ice, but only if warming slows. Should warming increase, then of course glacier ice is a threat. Inevitably, some permafrost will continue to thaw and produce greenhouse gases, but by then, hopefully, humankind may have adapted technologies to offset this. But it remains true that much of the Arctic landscape has already undergone irreversible change through coastal erosion, through shrinking glaciers, through shrinking sea ice, through slope instability and subsidence. But it will remain forever a zone of haunting natural beauty. Thank you very much for listening.